Right now, somewhere in the universe, a signal is firing. It lasts less than a blink, a few milliseconds, and it's gone. But for that tiny moment, it can be so bright in radio waves that it overwhelms the sky. And the terrifying part is this. Some of these signals come from billions of light years away, meaning whatever made them had enough power to be detected across the universe in a burst shorter than a heartbeat. They're called fast radio bursts, FRBs. And tonight, we're not doing a slow lecture, we're doing a chase. Because this mystery has 3 moments where the story completely flips. First, the burst that shouldn't exist. Second, the signal that repeats like a living engine. Third, the smoking gun event that happened inside our own galaxy and changed the entire case. And after all of that, one question remains. Are FRBs one phenomenon or many different engines wearing the same mask? Stay with me to the end, because the final implication isn't just what makes FRBs. It's what FRBs reveal about the universe, because they may be showing us that the sky has been screaming this whole time, and we were simply not listening. Prepare yourselves. We begin. Act 1, the discovery, the burst that started it all. It began as a single spike in the data. A radio telescope in Australia recorded a pulse only a few milliseconds long. At first glance, it looked like many other radio events, but one feature made it impossible to ignore. The signal was dispersed. Here's what dispersed means. Space isn't perfectly empty. It's filled with thin gas, and that gas contains charged particles. When radio waves travel through that plasma, lower frequencies slow down a little more than higher frequencies. So instead of arriving all at once, the burst arrives like a stretched-out chirp. High frequencies first, low frequencies last. That delay is measurable, and the more plasma the signal travels through, the bigger that delay becomes. So dispersion is like a distance clue. Astronomers looked at the dispersion of that burst and realized something chilling. The signal had traveled through too much material to be from inside the Milky Way. It looked extragalactic, beyond our galaxy. And if that's true, then a single millisecond burst was blasting through intergalactic space and still arriving loud enough to be detected on Earth. That first famous event became known as the Lorimer burst. And instantly, astronomy had a new mystery, because one burst could be a weird fluke. But if the universe produced these things more than once, then the sky was hiding something violent. The doubt phase and why it matters. For years, the scientific world argued. Some researchers thought FRBs were real. Others suspected interference, because radio telescopes pick up everything. Satellites, airplanes, electronics, even weird local signals that can look cosmic. And then, the embarrassment. Some burst-like signals were traced to a very human cause. Not alien, not cosmic, microwaves. That discovery didn't kill the FRB idea, but it poisoned the scene with doubt. So scientists raised the bar. They said, if FRBs are real, prove it properly. Not just, we saw a burst. They needed localization. They needed to pinpoint exactly where in the sky it came from, identify a host galaxy, and show it truly came from far beyond the Milky Way. But there was a brutal problem. FRBs don't politely repeat on schedule. They appear suddenly and vanish instantly. Catching one is like catching lightning, with a camera pointed the wrong way. So for a while, FRBs stayed in a strange limbo, too intense to ignore, too brief to easily confirm, until the universe delivered a plot twist. The twist, one repeats. One of the most important moments in the entire story is this. An FRB repeated, again and again. This object became famous as FRB 121102, the first well-known repeating fast radio burst. That single fact shattered the simplest explanation. Because if FRBs were one-time explosions, the source would be destroyed. A repeating FRB meant the source survives. It meant there's an engine out there capable of producing enormous bursts, over and over, without dying. And that split the mystery in two. Some FRBs repeat, some don't. So either we had multiple causes, or one cause with multiple modes. And FRB 121102 did something else even more unsettling. When astronomers studied it deeper, they found it lived in an odd environment, and it seemed connected to a persistent radio source nearby, like a constant glow in addition to the bursts. This wasn't just a burst. It was a system, a place, a violent neighborhood, And that took FRBs from weird spikes to a serious cosmic phenomenon.
The promise of the hunt. Now the hunt changed. The goal wasn't just to detect FRBs. The goal was to catch them in real time, to triangulate them, to connect them to galaxies, to measure their distances, to map their environments. And as detection tools improved, the universe started doing something terrifying. It started showing us that FRBs weren't rare. We were just bad at seeing them. And once we got better, the sky began to fill with bursts. And what scientists discovered next changed everything. ACT2, accumulating evidence. Part A, observable signatures. To understand why FRBs exploded into fame, you have to understand what happened when new instruments came online. Instead of one big telescope staring at a tiny patch of sky, astronomers built systems that could watch huge areas at once and detect bursts automatically. Projects like CHIME in Canada and ASKAP in Australia dramatically increased detections. Suddenly, FRBs weren't occasional. They were frequent. And that gave scientists enough data to build a real evidence case. Here are the signatures that made FRBs undeniable and made the mystery deeper. Evidence 1. Duration. FRBs are fast. Many are only a few milliseconds long. Some are even shorter in their fine structure, with microbursts inside the main burst. When something is that fast, it limits the size of the source, because the source can't be bigger than the distance light can travel during the burst. Millisecond timescales mean the emitting region is incredibly compact. That points toward compact objects. Neutron stars, black holes, white dwarfs under extreme conditions. Evidence 2. Dispersion measures that exceed the Milky Way. Many FRBs have dispersion so large it cannot be explained by the gas in our galaxy. The extra dispersion comes from intergalactic space and the host galaxy. This implies deep cosmic distances for many bursts. This isn't a local glitch. It's a universe-scale phenomenon. Evidence 3. Extreme brightness temperature. In simple words, the bursts are too bright, too fast, and too compact to be ordinary thermal radiation. This typically implies coherent emission, like pulsars produce. That again pushes us toward neutron stars and magnetized plasma. Evidence 4. Scattering and signal tails. Some FRBs arrive clean and sharp. Others arrive smeared, with a tail, as if the signal bounced through turbulent plasma. That tells us the local environment around the source can range from calm to chaotic. Some sources seem to live in clean space. Others live inside storms. Evidence 5. Polarization. Many FRBs are polarized, meaning the radio waves have an organized orientation. That implies strong magnetic fields shape the emission. And if you measure polarization carefully, you can learn about magnetism between the source and us, which means each FRB isn't just a mystery. It's a probe, a scanner, a flashlight shining through the cosmic fog. Evidence 6. Localization to host galaxies. This was the turning point for credibility. Once enough FRBs were precisely localized, astronomers could identify the host galaxies. And that's where things got uncomfortable, because the hosts were not all the same. Some FRBs were found in small star-forming dwarf galaxies. Some were found in large galaxies. Some were located in active star-forming regions. Others were found in calmer areas. If FRBs were one single type of event, we'd expect one pattern. But the sky gave us diversity. And diversity is a warning sign. It suggests multiple source types, or one source type that can appear in very different ways. And then we got a discovery that turned diversity into impossible, because one FRB showed up somewhere it shouldn't. But before we get there, we need the next layer of evidence, because the strangest FRB clues are not in where they come from, but in how they behave. And this is where it gets strange. Part B. Deeper implications. Repeating FRBs changed everything, because repetition lets you do something you can't do with one-offs. You can study patterns. You can compare bursts. You can look for cycles. You can watch a source over months and years. And when scientists did that, they discovered behaviors that felt almost unreal. Evidence 7. Bursts that cluster. Some repeaters don't burst evenly. They fire in storms. Multiple bursts within minutes or hours. And then silence for days. That suggests the engine isn't always active. Something switches it on and off. Evidence 8. periodic activity windows. Some repeaters show cycles. For example, a repeating FRB can become active every certain number of days, then quiet again. That hints at an orbiting companion, or a precessing beam, or a changing environment. It's the kind of pattern you see when a source is rotating, wobbling, or being modulated by something else. Evidence 9. Extreme Faraday rotation. This one is crucial. Faraday rotation is what happens when polarized radio waves pass through magnetized plasma. The polarization angle rotates. If that rotation is huge, it means the signal traveled through a region with intense magnetic fields and dense plasma. And one famous repeater showed signs of an environment so magnetized it shocked researchers. The implication was clear. At least some FRBs are born in extreme magnetic neighborhoods, not normal space, not a quiet galaxy, something like a supernova remnant, a dense nebula, or even near a massive black hole. Evidence 10. Frequency drifting subbursts. In some repeating FRBs, each burst breaks into multiple components that drift in frequency over time, like sliding streaks across a radio spectrum. This is not what you expect from a simple blast. It suggests structured emission and complicated plasma effects. It's like listening to a signal that is being shaped while it travels, either by the engine itself or by the environment around it. Now here comes the impossible location clue. One FRB was localized to a globular cluster in a nearby galaxy. Globular clusters are ancient. They are packed with old stars. They are not places where massive stars are being born today. So why would an FRB source, often linked to young, highly magnetized neutron stars, be in a place that old? This single observation didn't just challenge one theory. It challenged the assumption that FRBs are always born from young stellar explosions. And right when the field was still processing that, the universe dropped the most dramatic clue of all. A burst inside our own galaxy. A burst from a magnetar. A burst that looked like an FRB's little brother. And once you accept that magnetars can do something like this, you have to ask, are magnetars the main source of FRBs? Or are they just one chapter of a bigger story? Because the case is about to become a trial. And every theory has to take the stand. ACT3, the big picture. Part A, the leading theories, ranked like a court case. Let's make this simple. To produce an FRB, nature needs an engine that can do all of this. It must be compact. It must produce coherent radio emission. It must sometimes repeat. It must sometimes not repeat. It must survive long enough for some sources to fire many times. It must occur in a range of environments. And it must be powerful enough to be seen across the universe. Now, here are the leading models. Model 1, magnetars. Magnetars are neutron stars with magnetic fields trillions of times stronger than Earth's. They are the strongest magnets known, and that magnetism stores insane energy. If a magnetar's magnetic field rearranges suddenly, it can release energy in a violent event called a flare. It can also cause starquakes, fractures in the crust that trigger magnetic eruptions. In magnetar models, FRBs come from magnetized plasma and particle acceleration. This model fits many observations. It fits repetition. It fits polarization. It fits extreme magnetic environments. It fits the idea of burst storms. And most importantly, it has the smoking gun hint. A magnetar in our galaxy produced a strong radio burst associated with an X-ray flare, and the radio burst resembled FRB-like behavior. That doesn't prove all FRBs are magnetars, but it proves magnetars can produce bursts in the right family. So magnetars became the front runner. But magnetars still struggle with some details. Some FRBs are extremely energetic if placed at large distances. Some FRBs seem to occur in environments that look old. So either magnetars can also form in old systems through mergers, or magnetars explain only part of the population. Model 2, neutron star. Binaries and orbital modulation. If an FRB source has a companion, another star, a neutron star, or a massive object, then orbital motion could create periodic activity windows. The companion's wind could shape the plasma environment. The beam could be blocked or unblocked. The burst could be amplified at certain orbital phases. This model helps explain why some repeaters have cycles, but it doesn't automatically explain the extreme magnetism unless the main engine is already something like a magnetar. So many binary models are really magnetars plus a companion. Model 3, black hole environments. Some FRBs show evidence of Extreme magnetized plasma, possibly consistent with regions near massive black holes. A neutron star near a massive black hole, or inside an active galactic nucleus environment, could produce extreme rotation measures. This model can match extreme Faraday rotation. But it doesn't naturally explain the overall population by itself, because not all FRBs come from galactic centers or active black hole environments. So black holes may be a niche environment for certain FRBs, not the whole answer. Model 4. Catastrophic one-offs. If some FRBs do not repeat, they could be cataclysmic events. Neutron star mergers. White dwarf collapse. Black hole neutron star. Interactions. Events that produce a single burst and then destroy the source. This model explains non-repeaters neatly. But the existence of repeaters means this cannot be the only explanation. So we come back to the uncomfortable conclusion. FRBs may not be one thing. FRB might be a category, a label we gave to a phenomenon that actually contains multiple engines. Now, we have to address the speculative options. Because when something is this bright and this weird, speculation appears. Model 5. Exotic physics. Cosmic strings. Dark matter. Interactions. Unknown plasma mechanisms. These ideas are interesting, but they require stronger evidence, because ordinary astrophysics already provides plausible engines. So in serious science, exotic physics stays in the possible but unproven box. And then there's the one people always ask about: artificial signals, aliens. So let's say this clearly. There is no solid evidence that FRBs are messages. Most FRBs look like natural astrophysical bursts. They do not show clear encoding. They do not repeat in message-like sequences. And when we find repeating patterns, they usually look like physical cycles, not intentional communication. So the responsible stance is, treat FRBs as natural unless we see something that cannot be explained by nature. That said, the fact that FRBs are so bright and so brief means that if a civilization wanted to be noticed in radio, events like these would be the kind of signature we would detect. So scientists keep an open mind, but they keep it locked behind evidence. Now the story turns toward the future. Because even if we solve FRBs, their real power might be what they allow us to measure. And that changes the entire value of the phenomenon. Part B. Why FRBs might become the most useful signals in astronomy. Here's the twist many people miss. FRBs are not just mysteries to solve. They are tools. Cosmic tools. Because an FRB is a sharp timestamp, a pulse that crosses the universe. And as it travels, it picks up fingerprints from everything it passes through. That means FRBs can be used to study the universe itself. First, the missing matter problem. Astronomers have long believed there is missing normal matter, baryons, that we don't easily see. Not dark matter, normal matter, gas spread thinly between galaxies. FRBs travel through that gas. Their dispersion measures how much plasma is in the way, so FRBs can help map the invisible matter between galaxies. Second, cosmic magnetism. Polarization and Faraday rotation can reveal magnetic fields in galaxies, in halos, and in intergalactic space. Magnetic fields are hard to map on large scales. FRBs might give us a new way. Third, precision localization. With better arrays and real-time triggers, scientists can catch FRBs instantly and point other telescopes at the same region. That could reveal optical flashes, X-ray flares, gamma bursts, or persistent radio sources. Multi-wavelength follow-ups are the difference between guessing and knowing. And the tools are getting better fast. New and expanding facilities, new detection pipelines, and next-generation arrays like the Square Kilometer Array, future deep synoptic surveys, and upgraded radio interferometers aim to detect and localize huge numbers of FRBs. As sample sizes explode, patterns will emerge. We'll separate populations. We'll connect behaviors to environments. And we may finally answer the core question. What are FRBs? But here's the climax we're building to. If FRBs are happening constantly, and we can only detect them now, then what else has been happening in the universe that we've been blind to? Because every time humans build a new sense, radio, X-ray, gamma, gravitational waves, the universe doesn't become simpler. It becomes stranger. FRBs might be the beginning of a new era where the sky is no longer quiet. Where space is no longer air, silent void, but a storm. And now we reach the last act, the part that isn't about telescopes. It's about reality. ACT4, The ultimate questions. Let's zoom out. Fast radio. Bursts are telling us something uncomfortable about our place in the universe. We like to imagine. The cosmos is calm. Stars shine. Galaxies drift. Everything feels slow. But FRBs are proof that the universe is violently active on timescales we rarely notice. In the time it takes you to blink, something across the cosmos can unleash a burst that crosses billions of light years. Now, think about what that really means. Every FRB we detect is a time capsule. If a burst traveled 2 billion light years, then we are witnessing something that happened 2 billion years ago, long before humans existed, long before Earth was what it is now. And yet that event still reaches us, still registers in our instruments, still changes our understanding. So the question becomes deeper than what causes FRBs. The deeper question is, how much of the universe have we missed because we weren't listening in the right way? And here's the next terrifying possibility. FRBs may not be the only hidden population. They may be the first major hidden population we've stumbled into, meaning there could be other classes of fast, violent signals in other wavelengths, signals that exist all around us, all the time, invisible to our current tools. Now, we come back to the split mystery. Some FRBs repeat, some don't. Some are born in wild star-forming regions. Some appear in old environments. So what does that imply? It implies one of two realities. Reality 1, there are multiple FRB engines. A magnetar engine for many repeaters, a catastrophic engine for many non-repeaters, and perhaps other engines for special cases. Reality 2, there is one engine type that can masquerade as many. An engine that can repeat. An engine that can go silent. An engine that can be born young, or formed later through mergers. An engine that can live in different environments. Both realities are possible. And both realities are unsettling. Because either way, FRBs are telling us the universe has more extreme engines than we expected. Now we address the question everyone whispers. Could any FRB be artificial? Here is the scientifically grounded answer. We have no proof. Most FRBs look natural. But if we ever detect an FRB-like signal that shows unmistakable encoding, structured repetition with information, or behavior that cannot be explained by physics, then everything changes. So far, that has not happened. But FRBs have taught us a lesson. The universe is capable of producing events so strange that even careful scientists momentarily hesitate. So we stay honest. We stay skeptical. And we keep watching. Because in astronomy, the next surprise is always one better than the last. And now we end where we began. With the scream. A millisecond. Flash. Across the universe. A reminder that the cosmos is not silent. It's alive with hidden violence. And we are only beginning to hear it. Conclusion. Let's retrace the journey. We started with a burst that shouldn't have existed. A millisecond signal so dispersed it pointed beyond our galaxy. Then the story flipped. One repeated. Again and again. Proving at least some FRBs come from a living engine, not a one-time explosion. Then the field found patterns. Clusters of bursts. Activity windows. Polarization. Signals twisted by extreme magnetic environments. Then the mystery split even wider. An FRB appeared linked to an ancient environment, suggesting some sources may exist where young star explanations struggle. And then came the most dramatic clue. A magnetar in our own galaxy produced a burst in the same family as an FRB. Not a perfect match to all FRBs, but a powerful hint that magnetars can do something very close. So where does science stand now? The cautious picture is this. Magnetars likely explain a large fraction of FRBs, especially repeaters. Some FRBs may come from different engines, possibly including catastrophic events for non-repeaters. And FRBs, regardless of origin, are becoming one of the most powerful tools to probe the invisible universe, its missing matter and its magnetic structure. But one thing is already certain. Fast radio bursts have changed the way we see the sky. Because they prove the universe is full of fast, violent events happening constantly. Events we didn't know existed until we built the ability to listen. And that leaves us with one final question. If these signals were here the whole time, what else is out there, waiting for us to finally notice? The universe is vast. The mysteries are endless. And the journey continues.